Welcome back, everyone. Following our previous deep dive into the foundational concepts of designing with nature, principles and patterns, where we explored how ecological intelligence informs regenerative design, we now transition our focus to the concrete application of these ideas within the critical context of urban planning and climate change. Today's lecture addresses nature-based solutions for urban resilience, establishing nature-based solutions, NBS, not just as an abstract ideal but as a pragmatic, living infrastructure essential for creating cities that can actively withstand and adapt to increasing environmental and societal pressures. Our discussion today will frame NBS as a mechanism to transform environmental, social, and economic challenges into genuine opportunities for sustainability and innovation in the urban environment, aligning urban management with nature's own regenerative processes to create synergistic co-benefits. This presentation will systematically introduce the nature-based solutions framework, beginning with a focused definition and clarification of why metropolitan areas urgently require this approach, especially in light of escalating climate threats and the need to achieve urban resilience. We will detail the core principles of NBS, emphasizing multifunctionality and the IUCN's criteria for successful implementation, before categorizing the spectrum of NBS types, namely green, blue, and hybrid infrastructure, and demonstrating their practical applications across essential sectors. Crucially, we will explore the multidimensional benefits NBS provide across climate adaptation, water management, biodiversity, and human health, using performance indicators, P1 P8, to quantify these benefits. Finally, we will conclude by examining the crucial role of integrated policy and collaborative governance, highlighting the utility of tools like geodesign, and illustrating their successful implementation through major international case studies, the Copenhagen Cloudburst Master Plan and China's Sponge City Program. By the end of this lecture, you should be able to clearly articulate the definition of nature-based solutions and explain why they represent a more efficient, long-term, and potentially cost-effective alternative compared to conventional single-purpose gray infrastructure solutions. You will gain the ability to recognize the inherent multifunctionality of NBS and analyze how this approach simultaneously addresses multiple societal challenges, such as flood risk, urban heat island effects, and biodiversity loss. Furthermore, a key objective is to equip you with the knowledge to identify the essential criteria for designing and governing effective NBS projects, including the necessity of ensuring a net gain to biodiversity and employing adaptive management strategies. This knowledge sets the stage for assessing how NBS contributes to achieving global agendas, such as the UN Sustainable Development Goals, particularly concerning resilient infrastructure, health, and climate action. Nature-based solutions are fundamentally defined as actions to protect, sustainably manage, and restore natural or modified ecosystems that address societal challenges effectively and adaptively, simultaneously providing human well-being and biodiversity benefits. This is an evolving concept, drawing on earlier frameworks like the Millennium Ecosystem Assessment, which provided a foundational understanding of ecosystem services. The European Commission defines NBS as living solutions inspired by, continuously supported by and using nature, which are designed to address various societal challenges in a resource-efficient and adaptable manner. NBS serve as an umbrella term, integrating diverse concepts such as green infrastructure, ecological engineering, and ecosystem-based disaster risk reduction. Crucially, they differ from traditional engineering by prioritizing resource efficiency, adaptability, and the creation of multiple economic, social, and environmental co-benefits, making them highly effective over long planning horizons. These actions aim to improve risk management and resilience while enhancing sustainable urbanization. Cities urgently need NBS because they stand at the nexus of rapid global change and escalating environmental hazards, making them highly vulnerable to shocks and stresses. Approximately 70% of global greenhouse gas emissions originate from urban centers, thereby contributing significantly to climate change. This intense urbanization, coupled with climate impacts like heat waves and increased flood frequency, leads to cascading system failures and places immense pressure on conventional gray infrastructure, which is often costly and brittle. NBS offer a vital pathway to urban resilience, which is defined as the capacity of urban systems to withstand and recover from shocks while positively adapting to transform toward sustainability. By integrating NBS, cities can achieve significant socio-economic benefits, including local ecological restoration, improved sustainability, and long-term productivity, often at a lower cost than replacing or expanding gray infrastructure for water management functions. 6. The successful implementation of NBS rests on a set of core principles, foremost among them being the necessity of multifunctionality. This demands that solutions must generate multiple benefits simultaneously, addressing multiple challenges such as flood control and amenity value in a single spatial intervention. The International Union for Conservation of Nature (IUCN) Global Standard for Nature-Based Solutions emphasizes 8 essential criteria, including the mandate that NBS design must be context-specific, meaning it must be appropriate to local conditions, culture, and ecosystem characteristics. Critically, implementation must demonstrate clear evidence of generating an overall net gain to biodiversity and ecosystem integrity. Furthermore, an essential operational principle is adaptive management, which requires solutions to undergo continuous monitoring, using metrics for performance indicators, learning, and refinement to ensure long-term effectiveness and resilience against ecological and climatic changes. NBS interventions are conceptually grouped into 3 types based on the degree of human intervention and ecosystem alteration required. Type 1 NBS focuses on protection and conservation of intact natural ecosystems, e.g., existing coastal wetlands, forests, to maintain their current levels of ecosystem service delivery. Type 2 NBS involves the restoration or management of degraded ecosystems or semi-natural landscapes, aiming to improve ecosystem services through extensive or intensive approaches. Examples include riparian corridor restoration, sustainable grazing practices, or large-scale soil conservation measures like living fascines, revetments with cuttings, that enhance soil quality and slope stability. Type 3 NBS involves retrofitting or creating entirely new ecosystems in highly modified, dense urban environments, e.g., rain gardens, constructed wetlands, green roofs. These Type 3 actions are most visible in built-up areas and are critical for introducing ecological functions where they have been completely removed. Green infrastructure serves as the terrestrial backbone for implementing NBS, defined as a strategically planned network of natural and semi-natural areas within and around urban areas. Green infrastructure employs vegetated measures like single-line street trees, urban parks, and green roofs, such as the Chicago City Hall green roof. It is highly effective for climate adaptation by mitigating the urban heat island effect. Green roofs and green walls significantly reduce ambient air temperatures in urban canyons through shading and evapotranspiration, providing cooling services. Additionally, urban forests and green surfaces provide crucial air purification services by intercepting airborne particles, thereby improving local air quality. Green infrastructure elements also contribute to climate mitigation by enhancing carbon sequestration in tree biomass and soil organic carbon. Blue infrastructure focuses on integrating and restoring urban water bodies and aquatic features to enhance the functional capacity of the natural hydrological cycle. Blue infrastructure solutions are fundamental for water balance regulation and hydrometeorological risk reduction, particularly under intensifying climate pressures. Examples include restoring floodplains, creating retention ponds, and daylighting buried streams. Historically, floodplains provided essential ecological functions, but many have been converted, reducing natural flood resilience. Restored floodplains act as natural storage areas, reducing flood peaks and offering habitat provision. Furthermore, blue infrastructure involves coastal protection measures, where natural habitats like mangroves and salt marshes provide physical barriers against storm surges and erosion, thereby strengthening long-term community resilience. In complex urban environments, hybrid blue-green solutions are typically required, deliberately integrating vegetative, green, elements and engineered water-focused systems, blue. These solutions often represent Type 3 NBS and are essential for retrofitting resilience into existing built areas. Examples include rain gardens and bioretention basins, which capture, filter, and infiltrate stormwater at the source, significantly reducing the load on conventional systems. Permeable pavements function similarly by allowing surface water infiltration. A key conceptual contribution of hybridity is the framework of interoperability, which explicitly addresses the necessity of connecting and functionally aligning new blue-green systems, designed for multifunctionality, with existing, often single-purpose, gray infrastructure, like combined sewer systems, for effective multi-system urban flood management. Successful implementation of decentralized low-impact development strategies, common in hybrid solutions, can substantially reduce stormwater management costs compared to traditional gray infrastructure expansion. NBS are indispensable tools for building climate resilience, offering a combined strategy for both adaptation, reducing vulnerability to impacts, and mitigation, reducing emissions. For adaptation, NBS address the urban heat island effect. For instance, increasing urban vegetation through green roofs, living walls, and trees provides cooling effects through shading and evapotranspiration. The resulting improvement in microclimate and human comfort can be measured using thermal indices. For mitigation, NBS contribute to the carbon cycle regulation by enhancing sequestration and storage in biomass and soils. Protecting and restoring natural areas is crucial for securing these carbon sinks. Furthermore, assessment frameworks are available to help practitioners evaluate the long-term climate-proof aspects of NBS solutions, ensuring they remain effective even under future climate extremes. NBS provide a holistic and sustainable approach to urban water management by focusing on restoring natural hydrological function, enhancing flood protection, improving water quality, P3, and promoting resource efficiency. Techniques such as constructed wetlands, retention ponds, and water decelerating green strips are widely implemented in contemporary practice. Constructed wetlands are highly effective and broadly accepted NBS for water purification, capable of treating domestic greywater or polishing effluent from wastewater treatment plants, and supporting water reuse in both municipal and peri-urban contexts. Effective water management also requires strategic, data-driven planning to prioritize interventions in areas contributing most to flood hazards, and ensuring that new systems, such as rain gardens, maintain their infiltration capacity over time to prevent drainage failures and associated environmental risks. NBS are inherently linked to ecological health, demanding that interventions lead to measurable improvements, ultimately seeking a net gain to biodiversity and ecosystem integrity. Urbanization typically results in habitat loss and fragmentation, which NBS counter by promoting structural and functional connectivity across the urban matrix. Tools exist to assess the potential for NBS to support biodiversity, such as criteria for tree selection in temperate urban climates and species-specific ecological performance indicators. Furthermore, measures involving multi-species vegetation on green roofs, and the protection of natural wetlands and coastal habitats, are crucial for providing habitat provision and supporting diverse flora and fauna. By sustaining essential ecosystem services, NBS enhance ecological resilience, strengthen adaptive capacity, and contribute significantly to long-term human well-being and overall urban quality of life. A core strength of NBS lies in their capacity to generate significant social and health benefits. Access to high-quality urban green and blue spaces is strongly correlated with improved public health, including demonstrable reductions in stress levels, often quantified by measuring salivary cortisol patterns. Exposure to nature, including urban forests and parks, is linked to a reduction in non-communicable diseases and improved mental well-being, particularly benefiting vulnerable groups like the elderly and children. Beyond health, NBS interventions enhance amenity value, increasing perceived restorativeness and fostering a sense of place. The collaborative co-design processes necessary for many NBS projects, such as establishing communal urban gardens, also strengthen social ties and local capacity, promoting social cohesion and citizen engagement. Planners must, however, mitigate the risk of green gentrification, where ecosystem improvements lead to rising property values and the displacement of low-income residents. Effective NBS implementation demands inclusive and integrated governance that actively breaks down traditional administrative silos, often referred to as silo mentality. Policy efforts must transition away from single-sector regulation towards coordinating action across environmental, planning, and housing departments. Governance must involve a quadruple helix of stakeholders, government, industry, academia, and citizens, through participatory processes like urban living labs to ensure solutions are locally tailored and publicly accepted. The EU Green Deal serves as a major policy driver, providing a legal and institutional framework with binding and non-binding targets that European cities are central to implementing. A crucial methodological support for integrated planning is geodesign, a computational framework combining geographical information systems, GIS, and design methodology. Geodesign provides a social and technical framework for problem identification and conflict resolution, enabling stakeholders to collaboratively visualize, evaluate, and compare alternative development scenarios in a multidimensional spatial context. This process enhances decision-making quality and supports systemic thinking in local policymaking. Despite the clear benefits, widespread NBS adoption faces several significant challenges. The primary barrier is the persistent lack of robust, quantitative evidence demonstrating the long-term effectiveness and economic valuation of NBS across all contexts. This gap makes it difficult to justify investment when traditional cost-benefit analyses struggle to adequately capture the non-economic and multifunctional benefits. Institutional inertia and fragmented administrative structures, silo mentality, often impede the necessary cross-sectoral collaboration, leading to high coordination costs. Furthermore, securing sustainable financial models remains critical. While public funding, e.g., grants, subsidies, is vital, leveraging private capital through innovative business models, e.g., green bonds, ecosystem services payment schemes, is necessary for scaling up. Practical barriers include the complexity of navigating multiple legal authorizations, e.g., water, planning, mobility, and the need to design NBS to be climate-proof against the very extremes they are meant to mitigate, such as drought or excessive heat. Designing effective NBS requires moving beyond merely aesthetic greening toward a rigorous, adaptive, and evidence-based planning process. The design process must start with a systematic diagnostic of the societal challenges and local biophysical conditions to select the most appropriate NBS type. Multifunctionality must be intentionally sought through design, pursuing synergies with existing infrastructure and ecosystems. Methodologies like geodesign support this by structuring the design process, making science-based assessments visually accessible to non-expert stakeholders, and aiding in the comparison of development scenarios, e.g., transformation scenarios versus current trends. Critical to long-term success is the integration of adaptive management principles, necessitating the establishment of robust monitoring and evaluation programs using specific key performance indicators to track performance across all co-benefits. P1 pages 8. This continuous learning loop ensures that local experience and traditional ecological knowledge inform future iterations. The Copenhagen Cloudburst Master Plan is a leading global example of translating NBS principles into city-wide infrastructure resilience against increased extreme precipitation events. Rather than pursuing the traditional gray infrastructure solution of expanding costly underground sewer systems, the plan employs a comprehensive, surface-level strategy focusing on blue-green solutions. The plan transforms public spaces into multifunctional water management systems, creating cloudburst roads, floodable public parks, and squares that temporarily store and convey massive volumes of water safely to the harbor. This approach not only significantly reduces flood risk but simultaneously generates crucial co-benefits, including enhanced recreational areas, improved aesthetic value, and localized cooling. The Copenhagen Cloudburst Master Plan demonstrates how disaster risk reduction can be successfully integrated with urban quality of life objectives, representing a fundamental shift in planning philosophy. China's Sponge City program represents a massive, top-down national initiative leveraging NBS, low-impact development philosophy to address critical urban water issues, including flooding, scarcity, and pollution, across numerous metropolitan areas. The central goal is to transition urban areas into sponges, capable of absorbing, infiltrating, retaining, purifying, and reusing rainwater, thereby mimicking natural hydrological processes. The Sponge City program implementation involves the large-scale integration of Type 3 NBS, such as green roofs, permeable pavements, and constructed wetlands. Crucially, the program is driven by explicit national policy and massive financial commitments for ecological protection and restoration projects. The program provides a powerful demonstration of how top-down governance can successfully drive the application of advanced international NBS concepts, including those aligned with IUCN standards, at a vast, interconnected, and urban scale, creating systemic resilience and contributing to China's ecological civilization goals. 21. In summary, nature-based solutions are critical and indispensable components for addressing the converging challenges of rapid urbanization and climate change. By translating the regenerative principles of designing with nature into actionable green, blue, and hybrid infrastructure, NBS offer multifunctional and inherently cost-effective alternatives to static gray infrastructure. Their immense value lies in the synergistic co-benefits they generate across ecological integrity, human well-being, and economic viability. Successful deployment, as exemplified by the strategic planning in Copenhagen and the sweeping scale of China's Sponge City program, relies fundamentally upon adaptive management, requiring continuous monitoring, integrated and inclusive governance, leveraging collaborative models like the quadruple helix and tools like geodesign, and a continuous commitment to developing the quantitative evidence base. Moving forward, overcoming persistent barriers, particularly institutional fragmentation, the complexity of financing long-term ecological investments, and the difficulty of valuing non-economic services, is essential to solidify NBS as the future of resilient urban planning. NBS function much like a natural immune system for the city, instead of building stronger concrete walls to resist every external threat. Like antibiotics, they harness and enhance the regenerative power of the ecosystem itself to absorb, filter, and adapt to stress, like vaccination and healthy living, ensuring the city remains healthy and functional in the face of constant change.